In the experiment one, we mentioned a problem about having a sound with some noise in it. We'll try to solve that problem here. For the solution, we are going to be using the Colab notebook. The data right now is in Google Drive. So we are going to go ahead with that. So first, what we need to do is we need to mount the Google Drive. So once I'm going to mount it, it said it's already mounted because before that I mounted on the drive. So in the first attempt, it is going to prompt a URL. When you're going to click a URL, it is going to ask for the authentication from your email. When you provide the authentication, paste the code here, your drive will be mounted. So now the original audio file which we have is in this path. So we can look at the sample which are present there. So let me play the sample. So you can see, right, his sound is kind of there. It's kind of a noise. So our attempt is to reduce this noise as much as we can. So I looked in the solution, how what we can do there. So there's a branch called digital signal processing, which we are going to use in order, to play with the sound signal. So now the DSP requires the input format to be in WAV, whereas our file is in M4A compression format. So first we need to do is we need to convert M4A format into WAV. This is going to be used. There's a library which calls Spider. So once we install the library, we are going to use this segment to convert M4 extension to WAV extension. And as you can see, it's already finished. It was a small file. So the file is again same. We can hear it. It's still the same file, just only the extensions changed. And now it is reduced to WAV format. So now we have file on disk. So next step, what we are going to do is we are going to read the disk into memory. So what we are going to do is the file is in serialized format. So it's in order to represent it into a digital format, we need to convert those numbers into 1 or 0 format, which could be understood by our algorithm. So there's already built-in libraries for that. We can use Wave library to open a Wave file. Now, before we go on, there are some theory which I want to discuss here, not in detail, but how sound is represented in a wave format. What are the conventions for that? So a sound is represented like any sound can be represented by sinusoidal waves. Means a number of sinusoidal waves comprising together to form the pattern which we are seeing right now. We are going to see the diagrammatic representation in a coming section, but for now, just assume it's a series of sinusoidal waves. So now each audio signal associated with these kind of attributes. So first attribute is channel. So it could be a single channel or double channel. So not much detail into it, but for now assume that we have two channels and we are only having sound out mono channel. By the way, it's related to left and right speaker, something like that. How much sound is being observed in both, and we can have a stereo for that. So not really important for this experiment. So it it like each sound is represented by having the integer assigned to it, and their range can vary between the number of bits assigned. So right now, the range of this audio signal is between this, which can be represented in power of 2 to the power of 16. So if we if we take if we shift this negative into positive direction, it would be something around 65,000 something. And if we take a 2 to the power 8, it would be approximately the same. So we need 16 bits to represent the complete representation, each signal for that. That's why it's a 16-bit signal. And in MPG file, there are different kind of things like 32-bit, 48-bit, 64 bits. It depends how much amplitude or the strength of signal, the quality of signal that you want to have. Now the next term which is there is a sample rate. So it's actually kind of important. Sample rate means what is the amount of samples we can take in a second. So it's kind of a frequency. Like if we take 1 second, how many samples are we taking in that 1 second? So the larger the sample rate is, the better it is. So it goes from can go to in kind of infinity. We can take infinite number of samples, but the point is there's no use of it. Uh, the reason is like human can hear uh, sound between certain level of frequency, which is this range. So we can take samples greater than the size, but if we are not going to notice them, what's the point of taking? That's why you said like 41,000 something kilohertz is the range that we should consider. That's a simple means, not too much, but that's going to come, in the future that I'm going to say. So next, just not important kind of thing. So now, so here in the code, what we're trying to do is first we are going to open the audio file. Then we are going to look at the parameters, like what's the parameter that there. Then we are going to read individual frame, and since it's a different format, and we need our output to be integer format, not in binary format. So we are going to use struct library convert the integers into binary format. So by running this, we said that it contains a mono channel. The sample width is 2. The frame rate is 44,100, which is the means max range that we needed. Number of frames means duration of our whole window is this one, like this many samples of number of frames we have in that audio file. And as you can see, we have seen, means we calculated like what's the maximum value of that frame wave and the minimum. And since the max and minimum is this, so it makes sense, right? It cannot, because we in the 16-bit integer we cannot have value maximum than that. So that's why we are getting a maximum and minimum in this also. If it were 30-bit 2-bit file, it would be in that range. So right now we have done nothing. It just redid the file, converted the binary digits into the integers that we need for processing. So this is just a series of integers, or rather a series of 6,76,864 integers. Okay, now here is the main thing which comes in picture. So what we now have is a sine wave, integers. We can operate on this data, but it's not efficient to operate on this data. The reason being, the data is again hard to manipulate. So what we are going to do right now is we are going to play with this data and apply Fourier on that. So what Fourier does? The Fourier role is the change of perspective. By change of perspective, I mean it converts the data from one domain into another, which is from time domain into frequency domain. And once we come from time domain to frequency domain, it becomes easier to operate on that data. So it's really easy to use. All we need to do is use this, like FFT pack.fft, which should be defined like here from sci-fi import FFT pack. So it's an inbuilt library. We don't have to do anything that. So it is going to convert this sinusoidal waves into a complex number kind of a format, which have like two different things. It will have a magnitude and phase. Okay, so what is magnitude and phase? So magnitude is like the energy, kind of the energy of each frequency, and phase is the angle. So we use this information to play with the signal. So like how we're going to represent that. So in order to explain that, let me show you the diagram. Probably that would be much easier to explain there. So here, so what we have done is we plotted some of the graphs based on our output data. So this is the original wave that we have. This is a spikes, like the whistle kind of a noise was there. There were three whistles and three sub whistles. So there are three different spectrum. So each represent the amount of amplitude that it has. So this is a time series data before applying Fourier. So once we applied Fourier, so we obtain data in frequency format. Now on the application of Fourier, we have two values. One is real value and the other is imaginary value. It should be on here, like here. So if we take an absolute like np.abs of this component, what we get is the frequency distribution, like how the frequency is spread across this signal or mp3 file. So this is a time domain data, the frequency domain data. Now what this signifies is this is the frequency, like 5000 series frequency is having this much energy or magnitude, and we can see like our majority of data is spread across this channel frequency from 20,000 to 30,000, or and there is a small there like 0 to 5,000 there. And here we have kind of a spread kind of a frequency, but not that important in magnitude wise. So this might be a noise or this might not be a noise. Right now we don't know that. Okay, so we have clipped the data in the which like spectrum what we can scan 0 to 41 4100 as mentioned above. Like this is the part where we are interested in. We are not interested in the whole spectrum, but if we need to visualize there's a whole spectrum. So as you notice that this is the spike here, but we have a similar spike here. So it's like it's the exact replica. If we divide this whole diagram in half, the left half is the exact replica of the right half. So we don't need right half. So this is due to phase component, like there's a complex conjugate which is happening here. So we can represent the whole signal by using first half. We don't need to take the other half because they're exactly similar to what we have already done. Now I might be wrong here, but I'm just from what I studied in this couple of weeks, this is what I'm able to get from here, that we can operate on this data. So now, so what we need to do right now is we need to play around with this domain, and this by changing this domain, this is going to get affected. Okay, so now here, these are the couple of good tweets which I have read, which in turn tell me that like how this is being affected. So now, how we are going to filter a signal? So either we can clip this region out, or either we can clip this region out, but we need some mechanism to do that. So if we place a rectangular window here, this data will be clipped out, and as well as this data. So these are low frequency components, these are high frequency components. So if we allow low frequency data to pass, and if we clip high frequency data, that's called low pass filter. If we allow high frequency data to retain and clip out low frequency data, it's called high pass filter. And a band pass filter is like if we allow a certain band to pass through it. So we can use anything here. So as I mentioned, if we place a rectangular here, we get our exact data that we need. But how should we apply a rectangle? So turn out the like rectangular in frequency domain is actually a sinc function in time domain. So we can use this information. Like Either we can operate directly on frequency domain or we can operate on time domain. So in frequency domain, we need to multiply this with our this way, or we can take this time domain data and we can converse with this signal. Now, they are just kind of a vice versa of each other. If we apply a convolution in time domain, it becomes a multiplication in frequency domain, and vice versa. That's why if we apply, if applying multiplication in domain is same as applying convolution in time domain. So that's just it. But we are not going to exactly use this, kind of like this, because as you can see, this signal is continue towards infinity. We cannot use the signal because applying this means taking samples up to infinity, which is actually not possible. So we are going to take some approximation of it. So what do I mean by approximation? That we are going to clip the surroundings, like we are going to clip the regions which doesn't matter much, and take the bulk of the signal. That's called windowing operation. And actually, this uh, link pretty much explain in a better way, like what it means. Here's a triangular filter. We can operate a rectangular filter. Like if we take only 21 values here, we end up having, approximate filter, which ideally behave like that. So there's a whole theory behind this, like which is much accurate window size. There is a couple of algorithms we can go into it, but right now assume like we have used some filter and we are going to apply on that because that's way of topic. So once we have the filter, what we are going to do is we are going to apply on our signal. So here is we have applied the signal. We said we don't need data after certain frequency. Okay, and this is the order, how much data, how much clipping we need onto the string function. And here is our scipy function to do that. So now let me show you first, like if we run this, what's the output is going to be. Like this is our filter. So as you can see, it's a high pass filter. It's allowing the high frequency be retained, but it's clipping, all the frequency less than that signal. So this, like first we go this here. This is our original frequency domain data. So it clip this region and it allows, only the major frequency to be retained. And so if we operate on frequency domain data, that means we have some effect, or almost the same effect on time series data as well, because these are replica of each other. So if we take the inverse Fourier transform of this data, what we'll get is, like in original data you can see bulky kind of a signal, but here you can say there's not that much crisp kind of a thing. So as you can see, let me just show you, this is a bulky line, whereas this is not a bulky line. As you can see, there's some information is out there. So on operating this, does it clip out the noise? Let's see. So actually it does filter out the noise. I'm not noticing any hiss sound right now. In the video you might be able to notice, because again, that's a recording and everything. So I'll be posting the inputs in the input mp3 and the output mp3, and you can listen to that. There's actually the whole hiss sound is gone now, and what I'm getting is pure signal. The reason I'm saying that is, if like here, let me just reverse this process. And now instead of retaining the signal, I'm trying to retain the hiss sound. Okay. So once I run that, so here you can see only the lower frequency component is retained. It's magnified, but it's same. It's 25, and here's the 25. So it's the same to the component. So now if I play this, So as you can see, right, we are only hearing the hiss sound and not the actual output. So this actually, segregation does clear, that does segregate the noise from signal. So it's a kind of a trial and error. I come, at this frequency by trial and error basis. And also something is funny is going on in this function, which right now I'm not able to understand because I'm trying to, I'm just coming up randomly with this number, and somehow, it's clipping a higher frequency range. Like it's not exactly 900, it's greater than that. So means I'm not much experienced that. I'm just getting used to. That's why it might be something funny, but it is doing the work. Like it is clipping out the frequency from the noise. So again, just we can just revert back to our signal and get the perfect voice that we're looking for. So we can again save this back to the drive, and yeah, we're done, I guess. So I'll be looking into a way to solve this better, but for now I think that will do the work. So anyway, thanks, guys.